Hi everyone, this is the next video, introduction into the first real chapter of this course. Just a very quick disclaimer. All of these videos, recordings are filmed in one take, and I don't really like you know I won't do retakes or anything, so there's gonna be arithmetic mistakes and I'm gonna stumble and I'm gonna mess up, but hopefully I can catch myself and fix those, and that's where it becomes, hopefully it becomes valuable to see step by step me kind of working through these problems and these ideas. So we're gonna start with the first unit or first chapter or whatever. We're talking about discrete signals. Okay. Um, so maybe some of you know this, some of you don't, but the idea of a discrete anything is you chop it up. So a continuous function, right, is what you're used to seeing. You're seeing x, and this is f of x, and at every point x, you say, here's the value, here's the value, here's the value, here's the value, and you literally do it for every point x, and you get a continuous smooth function. Okay, a discrete function is, you don't do it for every single value of x, you do it every 1 second, or for every one. So you do it for x equals 1, you say, hey, I'm here. At x equals 2, I'm here. At x equals 3, I'm here. And here is your discrete function. So there's no line connecting the two, because you're ignoring all the points in between here. You're just keeping it discrete. Okay? So that's kind of the classic intuition you should have about, okay, instead of undoing everything, I'm just going to erase. That might be smarter. Okay, so let's formally define this a bit. Okay, so what is a discrete signal? It is a function from where to where. It is a function from the numbers in this set. So I'll explain what this means, from 0 to n minus 1, and it maps every point here to a real number. Okay, so what does this mean? We call it x of n. So this says my x is a signal that takes in an n value from this set, where this set 0 to n minus 1 is 0, 1, 2, 3, n minus 2, n minus 1. So if n is 16, this is going from 0 up to 15. Okay, so it's going to take every point and it's going to map it to a real number. So let's do an example for n equals, I don't know, 8, right? What is our x of n going to look like? Well, here's going to be our n, here's going to be x of n, and we're going to go from 0, 1, 2, 3, all the way up until 7, right? And this is just because we define it going from 0 to n minus 1. You could also go from 1 to n, and we'll see how that's kind of the same thing later. But it's going to take 0, it's going to say x of 0, I'm going to map you to some number. 1, I'm going to map you to some number, another number, and this is how we make our discrete signal. So that's what it looks like. Remember, we don't connect the dots because it's a discrete signal for a reason. Okay. More important later on is that I said here that it maps, from n to a real number. So it maps a point here to a real number. Later on, this can actually become a complex number, or whatever the symbol is for, I kind of forget, whatever, complex number. But those aren't too different. So for now, we'll just define it to the real numbers. Okay, that's kind of a less important thing. Okay, so we know what discrete signals are. Let's just, give an example. So the most simple one is the constant function. Okay, so that's defined as x of n equals c for all n. This sign means for all. Okay, so the big idea, or one key thing you have to remember, is when you talk about a discrete signal, you have to define this big N. This big N is saying how many time samples are you taking. So for example, here we said big N was 8, so we went from 0 to 7, right? We have to say that because yes, we can have an infinitely long signal, but we like to think about finite length signals, because at the end of the day, we're in the real world and we want to have these defined numbers. So let's set again n equal to 8 just for this example, right? But what is the constant function going to look like? It's going to say, okay, every point is going to be mapped to a constant c. So let's say c is right here. You're going to be mapped to c. There should be 8 of those. You're going to be mapped to c, and that's what our function looks like. Okay, simple. These are probably three of the most common ones you'll see. The second one is a square pulse. So we call this a square pulse. Okay. This one is going to have a width of, let's call it m. Okay. So the way we write this is square pulse with width m as a function of n. So remember, all of these are a function of n, right? Because we take in an n value on our x-axis. So how is this defined? So the square pulse of width m is defined as 1 if your n is between 0 and m, and then 0 if your n is bigger or equal to m. Okay, so what does it look like? Well, we can obviously think about the graph. I probably should have switched the colors here, but I think it's too late to do that now. So here's n here. Let's say, again, big N is 8. And so big N is not in here at all, but big N is kind of where we cut off our sampling, so where we stop. So I'll just put a bunch here. And let's say this is the specific m value we choose. So for everything up until here, it's going to be 1, right? So when n is between 0 and m, so not including, so we stop here. And then right as we hit m, we go to 0. Okay, so again, this is a discrete signal. Let me just do this in red so it's clear. So here's what our signal looks like. Boom, 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 right? This is a discrete signal, so we never connect the dots. But if you were to connect the dots, it would look like, there we go, like a pulse, right? A square pulse. Technically it's a rectangle, but that's irrelevant. We still call it a square pulse. Okay, the last one, and maybe the most important, is called the delta function. Okay, you're gonna see this throughout the semester. It's a very common function. It's defined as delta of n. It's 1 if it's 1 if your n value is 0, and then if anything else, it's 0. Okay, so basically what the intuition for a delta function is that you're gonna have delta of something. In this case, it's n, but it could be anything. This becomes 1 when the stuff inside here equals 0. That's, if you know that, you know what a delta function is. So here, what is this going to look like on a plot? Again, it's going to be 1 when our n is 0. So only at this point is it going to be 1, and everywhere else it's going to be 0. Okay, so that's a delta function. It's like a spike. Okay, so those are 3 examples of discrete signals. Let's now move on to a few more definitions. Okay, because we're talking about discrete signals, we like to have some numbers for the way we work with these. So we have a number that's called TS, which is the time. So TS is the time between samples. Okay, so this says, okay, right, when I'm creating my signal, 0, 1, 2, 3, 4, 5, 6, these are my time steps. Okay, in real life, I might find out this value and say it's this, and then my next value happens 0.2 seconds after. Right? So basically every 0.2 seconds, I'm taking a new sample. That's my value of TS. Okay? So TS is the time between samples, let's say n and n plus 1. Okay? So between any 2 samples, it's the amount of time that has lapsed between when we hit sample and sample again. So you can think of sampling a signal as just repeatedly clicking a button. Every time you click a button, you find out the value at that point. Then you click another button, find out the value. Then you click another button, find out the value. So TS is the time in between when we're clicking those buttons. Okay. From this, we also define the frequency. So in general, right, we know period and frequency are inversely related, right? The period of something is the amount it times, so the amount of time. So if we have a wave, okay, 1, 2, 3, 4. This is just for an example. If my wave looks like this, okay, the period says how long does it take for one whole cycle to elapse. So to start from here, to go all the way up to here, it looks like it takes around whatever 2.5 or 3 seconds. Okay, frequency is the inverse of that. It says in 1 second, how many cycles have we completed? So they're inverses of each other. This is a good relationship to know. So because we have TS, we also have FS, which is a 1 over TS, which is the sampling frequency. Okay, so TS is the time between samples, FS is the sampling frequency. It's basically how many samples are we doing per second. Okay, so higher sampling frequency means boom, I'm tapping that button really fast. I'm taking a lot of samples. Okay. For some problem solving, it's good to know that if we want to, right now this is as a function of n, right? But in the real world where we're doing this over some time, so we can always calculate our current time as t is our current time is n times ts. So this says, hey, if we're at the 5th sample, the amount of time is the number of sample we're at multiplied by how long we wait in between each sample. And that should make perfect intuitive sense, right? You take the amount of time it takes between each sample multiplied by the number of times we've sampled, and that's going to be the time that we're at, right? Similarly, you can think of an expression for the total time, right? And the total time of this whole thing will be big T equals big N times TS, right? Because big N at the end of the day is the number of samples we're completing. Big N is whatever the number our last cutoff is here. So it's when we stop. So big N times by TS will give us the total time T of this whole signal that we've sampled. Okay. I'm probably going to stop here for this video, and then in the next video we'll start talking about cosines and sines and whatnot, because I don't want to make the videos too long. But hopefully you enjoyed, and see you in the next one. Bye-bye.